A warm welcome to part 2 of the lecture on functions. In the previous lecture, we looked at the constant function and the identity function. In this lecture, we shall continue to look at some other examples of standard functions. Let us start with the absolute value function. F is a function from R to R such that x gets mapped onto absolute value of x, which is denoted by this double bar symbol and read as mod of x. It is defined in the following way. Mod of x is equal to x if x is greater than equal to 0 and minus x if x is less than 0. The domain of this function and the codomain of this function are same, which is R. The range of f, as you can verify, is this semi-closed interval 0, infinity, which is obviously not equal to the entire real set R. It is an interesting exercise to show that modulus of x plus y is always less than equal to modulus of x plus modulus of y for all x and y belonging to R. It is easy to verify that this inequality is trivially true if either of x or y are equal to 0. In the other case, when x and y are both non-zero numbers, one should use the definition 1 and consider separately the cases when x and or y are positive or negative. And one should establish this inequality in each of these 4 separate cases. Let us understand the geometrical interpretation of the absolute value function. Mod x represents the distance of the point x on the real number line from the origin. So if we plot the real number line and locate the point x on it, modulus of x is nothing but the distance of the point x from the origin, as you can easily see in this figure. As an illustrative example, let us consider modulus of 2.5. According to the definition, since 2.5 is a non-negative, in fact a positive number, its absolute value is just equal to 2.5, which is also equal to the distance of the point 2.5 from the origin on the number line. Similarly, modulus of minus 1.5 will be equal to 1.5. Let us consider the polynomial function. F is a function from R or C to R or C, such that x gets mapped onto an x to the power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus all the way up to a naught, where these constants an minus 1, an minus 2 and so on are either members of the real number set or the complex number set. And also we require that an should not be equal to 0. In this case, f is said to be a polynomial of degree n in the real or complex variable x, depending upon what our domain or codomain sets are. We ask the following question: what is the range of f? The answer to this question depends upon whether the domain and codomain is C or R. The range of a non-constant polynomial function in a complex variable is the whole codomain, that is the set C. This is what is known as the fundamental theorem of algebra, the proof of which shall not be our concern. By a non-constant polynomial, we mean that at least one of the coefficients a1, a2, a3 up to an, at least one of these coefficients should be a non-zero real or complex number. If the function f is a polynomial in a real variable, its range need not necessarily be the whole of the real number set. For example, consider the function fx equal to x square plus 1. The range of this function is the semi-closed interval 1, infinity, which is not equal to the entire real set R. Let us consider the real exponential function. F is a map from R to R such that x gets mapped onto e to the power x. The domain and codomain of f are R, and the range of f is the open interval 0, infinity. Let me just mention that I have not rigorously defined what e to the power x means. A rigorous definition of the same will require more sophisticated tools and machinery from mathematics, which is not our present concern. May I also add that instead of R, we could have had the domain and codomain sets to be the set of complex numbers C, which means there do exist complex exponential functions as opposed to real exponential functions. However, the behavior of complex exponential functions is significantly different from their real counterparts. As we shall see later, the complex exponential function is a periodic function, whereas the real exponential function is a strictly increasing and aperiodic function. Next, let's move on to see the real logarithmic function. F is defined from the open interval 0, infinity to R, such that x gets mapped onto ln of x. The domain of f is the open interval 0, infinity, which means the function f here, which is the real logarithmic function, is not defined on the whole real number set. It is only defined for strictly positive numbers. The codomain of this function is R, and as you must already be familiar with, range of f is the whole real number set R. Next, let's see some trigonometric functions like sine, cos, tan, etc. F is a function which maps R to R, or as we will see in complex analysis, C to C, such that x gets mapped onto sine x, or x gets mapped onto cos x gets mapped onto tan x, and so on and so forth. I hope you all are aware of these standard basic trigonometric functions during your encounter with trigonometry in your school days. The range of these trigonometric functions, as you must be knowing, is the following. Range of sin x and cos x is the closed interval -1 to 1, whereas the range of the function tan x is the whole real set R. Next, let us consider what is called the greatest integer function. Here also f is a map from R to R such that the number x gets mapped onto an integer m. So m belongs to the set of integers denoted by z, with the following property. M is less than equal to x and x is strictly less than m plus 1. So basically, in order to find the greatest integer function of a number x, you need to consider all those integers which are smaller than or equal to x, and then from among that set of integers, choose the largest integer. Instead of writing m, we used a notation square bracket of x to denote the greatest integer function. Let us consider some basic examples. The greatest integer function of, say, the number 2.5, as you can verify, is 2. Why is that? Let us consider the set of all integers less than equal to 2.5. So clearly that set will comprise of the integers 2, 1, 0, -1, and so on and so forth. The largest integer in this set is 2, and therefore the greatest integer function of 2.5 is equal to 2. Similarly, let us consider the greatest integer function of the number -0.5. The set of integers less than equal to -0.5 is -1, -2, -3, and so on. The largest integer in this set is -1. So the greatest integer function of minus 0.5 is equal to minus 1. There is a nice way to find out the greatest integer function of x on the real number line. We first locate x on the number line, and starting from x, we start moving towards left. The first integer we encounter is my greatest integer function, square bracket of x. Let us illustrate this. So this is my real number line. This is the origin. Say x is equal to 2.5. We locate the point x corresponding to the number 2.5 on the real line, which is this point. And we start moving towards left from x. Quite obviously, the first integer which we will encounter will be 2. And therefore, 2 is equal to the greatest integer function of 2.5. Similarly, let's consider x equal to minus 0.5. Starting from x, we start moving towards left. The first integer which we encounter is minus 1, and therefore greatest integer function of minus 0.5 is equal to minus 1. Now let us consider what is called the least integer function. F is a map from R to R. X gets mapped onto a number m belonging to the set of integers such that m minus 1 is strictly less than x and x is less than equal to m. So basically, in order to find the least integer function of a number x, we look at the set of all integers which are greater than or equal to x, and from that set of integers we choose the smallest one. For example, let us consider the least integer function of the number 2.5. We have located the number 2.5 on the real number line, and we start moving towards right instead of left. The first integer which we encounter, which in this case is equal to 3, will be the least integer function of the number x. Similarly, let us consider the case when x is some number between minus 1 and 0. The least integer function of x will be, as you can clearly see, 0, because 0 is the first integer which we will encounter when we start moving towards right from x. It is worth mentioning that the range of both the greatest integer function and the least integer function is the set of all integers z. Finally, let us consider the relation x square plus y square equal to 1, which implies y is equal to plus or minus under root 1 minus x square. As you can easily verify, a particular value of x, say 1 by 2, is mapped onto two different points, namely plus or minus under root 1 minus x square. Hence, the image of x is not unique. Therefore, as per our definition, this does not qualify as a function, because the point x equal to 1 by 2 is simultaneously mapped onto two distinct points, namely root 3 by 2 and minus root 3 by 2. Let me stop at this point. In the next part of the lecture, we shall define the graph of the function, and we shall study some different classifications of functions. Thank you.